I will be talking is the topological phases of the Kitaev-Hubbard model, but topological phases has been already mentioned here in the form of Arvind Kejriwal by Vijay Sonai. So, most of the talk what I am going to explain who is Arvind Kejriwal and what is that phenomena. So, topologic. So, for the sake of completeness, I will describe just briefly what is topological phases. So, if you want to understand topological phases, let us first know non-topological phases. I apologize Landau, because generally we should say Landau phases, but I am now going to tell non-topological phases because this is era of topological phases. So, basically the phase of the matter we characterize by some kind of a internal patterns or internal structures or internal order, which we call order. And this order is associated with either by symmetry or breaking of a symmetry. So, the great Landau used these relations between the order and symmetry. He developed a theory and he explained all the phases, most of the phases what we know till 1980. He explained everything, but as people say that nature never stops surprising, but I am saying is not correct statement. Correct statement is that nature reveal you thing when you are ready. So, if you look the topological development in mathematics, Michael Atiyah, Professor Seshadri from TFR, all those big name, they became a big because the great work of mathematics in topology. So, when humans are ready, nature reveals. So, topological phases, how do you characterize? Generally, we characterize topological phases by assigning some sort of a universal quantum number or topological invariance. And all those phases which has this universal quantum number or topological invariant, same we say the same phase and we can move smoothly from one phase to other phase. Second thing, as in experiment, how do you probe these phases? So, it is a very important to understand topological invariant and then corresponding observable. So, in fractional quantum Hall state, which is an example of a topological phases, observable is actually charges and statistics of Horcruxes of electron, because electron there splits in many parts. That is like in fractional quantum Hall state, actually electron is a Voldemort. In a topological insulator, parity of a Dirac cones is observable, and Z2 invariant is actually invariant, topological invariant. So, once you know the topological invariance, you have to actually correspond or you have to look some observable in the experiment and you can see that. Now, once you know what is the topological phases, then you can ask how many possible kind of a topological phases can occur. So, I can list you 4 type of topological phases. Generally, I am not going to in detail that in a quantum system there will be a gap system and there will be a gapless system. I am taking only example of a gap system. So, consider a physical system which you can describe by some Hamiltonian edge, and that Hamiltonian actually depend on some parameter space, depend on some set of parameters, and assume that parameter actually you are changing in the parameter space. If you change the parameter in the parameter space along some curve, adiabatically or non-adiabatically, it does not matter. If non-adiabatically, then non-adiabatic type of object, geometric object you can construct. So, what you find? One possibility that you have a topological phase which you characterize by some topological invariant, and this topological invariant can take a discrete value. You change a parameter, what happens? As you change the parameter, there will be a region of a parameter space in the where this topological invariant will not be defined, and when the transition occurs, the gap closes. So, this is the example, the topological transition by the gap closing and the region of a parameter space where the topological invariant will not define. Second possibility, this is example topological Fermi liquid to the anomalous quantum Hall state. Second example, you can think a topological in a state you can change in the parameter space, and what you find, and some point in the parameter space gap closes, and then again you enter into the different topological state. So, this is also example of a gap closing, but the topological invariant is ill defined at that point. Third example, you can think you can get a topological transition without gap closing. So, suppose you have a parameter space and here the gap closing, you can take a detour along this path, avoiding this point where the gap is closing. What happens? The phase can go from one topological phase to other topological phase. The price you pay is like along this path, topological number is not defined and symmetry breaks. Fourth possibility can happen that topological phases you take it and you can go without gap closing and throw out the parameter space, topological invariant well defined. This is the example. We are submitting this paper is called, I request you to all of you to read that, the first order quantum Hall transition in Hofstadter butterfly system. This after school we are going to submit that. So, once topological phases is described, I am going to start my talk. So, I am going to describe now what is Kitaev model. So, before Kitaev model, you know that even the Bill Gates know the how electron hops on the honeycomb lattice, because he funded the graphene. So, when electron hops on the honeycomb lattice, so electron hops on the honeycomb lattice, what you find these dispersion relations, and two things you can see. So, you have two bands and these two bands are touching. I am not going to explain why it is a Dirac electron, a Dirac hole and Dirac points, because everybody knows, even Rekshawala know. So, that is not a problem. So, now what I want in this case, these two bands are spin degenerate. What I am going to do actually, I am going to split the spin degeneracy by the following process. So, you have already a hopping T, I am going to introduce extra hopping T prime, but this time when the electrons hops along the Z link, we project out X is component of a spin and Y component of a spin. Similarly, you can do Y, Z. So, in this process what happens, actually spin degeneracy is lifted, instead of a 2 bands, you will have a 4 bands. So, you can see here at T prime equal to 0, you have just spin degenerate 4 bands, and at T prime 0.5 we have plotted here is like a 4 bands 1, 2, 3, and T prime equal to 1, you find this clear gap in the this bottom band and the top band. So, when you turn on T prime, two things happen, the bands spin degeneracy lifted, as well as you can see you have a Dirac points 1 and 2, which we call K and K prime. Now, you find extra Dirac points. So, I have a Dirac points in the Benoit zone here, extra 3 Dirac points appear, which we will discuss later. This is 2. And second thing, at what you see T prime, the gap open. So, you can see that as you change T prime, there is a metal to insulator transitions. Since you are lifting you are applying a spin dependent hopping, the time reversal symmetry is broken. So, some kind of a geometric object you can construct in Hilbert, projected Hilbert space. So, that geometric object at quarter filling, if you look here, is a Berry phase, and as you turn on this T prime, this Berry phase quantize and becomes a Chern number. So, here you see topological transition of first kind what I described, that is this is called topological Fermi liquid to the anomalous quantum Hall state as a function of T prime, and everything is happening at u equal to 0. Okay. So, this is this red this point in the Benoit zone is Dirac points. Why is red and blue? So, this is the Dirac points when T prime equal to 0. As you turn on T prime, extra 3 Dirac points appears. And if you, this Dirac point is a topological object, if you ask circulation of a this phase of a wave function, what you find, this Dirac point, the old Dirac point's chirality in these directions, and the new Dirac point's chirality is in opposite direction. So, when this Dirac point has a chirality plus, then red will be minus. So, this is the, that is why red and this. As you change T prime, what happens? This Dirac point starts moving, and then at this point the cross, green cross, it merges. So, it is an example of, so what is happening here, as you T prime you change, Fermi surface topology is changing. So, Fermi surface topology is changing, then in the literature what we call Lifshitz transitions. So, at T prime, some T prime critical, what is happening in this system, topological Lifshitz transition is occurring. So, I am going to, so topological Lifshitz transition is characterized by topological change of Fermi surface in the Brillouin zone. And at the Lifshitz transition exhibits singularity in the thermodynamic potential. The change in the Fermi surface topology induces singularity in the density of states. So, now I am going to show you the singularity in the density of states. So, when T prime equal to 0, this is nothing but a graphene, and you know that density of states of graphene near omega equal to 0 is behave like omega. But since this is a Lifshitz transition at T prime 1 by root 3, what you expect that it should be the exponent of, instead of 1 it should be different, and what you can see from this curve, exponent is half. So, this is an example of Lifshitz transitions, and that Lifshitz transition occurring at T prime equal to 1 by root 3. See, now I am going to construct a few objects, geometrical object. That one geometrical object everybody knows here, that is Pancharatnam-Berry curvature. So, Pancharatnam-Berry curvature characterizes how the phases of single particle wave function twist over the Brillouin zone. Pancharatnam, if you have any question regarding this name, you can ask. Pancharatnam-Berry curvature becomes singular at the point where two bands touch due to the multivaluedness of a wave functions. Pancharatnam-Berry curvature is singular at the Dirac points. We call it a Dirac puncture in the Brillouin zone. So, Dirac point is nothing but a puncture in the Brillouin zone. The integral of a Pancharatnam-Berry curvature over occupied wave vector is Chern number, and you have been listening this Berry curvature, Berry phase in the Vanderbilt talk. So, if you ask what is the Chern number of these 4 bands, so it is a +1, -1, +1. That is why when you come from here to here, this is a topological transitions, and T prime 0.5, I have shown the Berry curvature plot in the Brillouin zone, and T prime equal to 1. So, the story is like this: at T prime equal to 0, it was a graphene, you have 2 Dirac points. As you turn on T prime, 8 Dirac points appears. When you reach T prime equal to 1, then Dirac point merges, and again it was 2 Dirac points. So, now I am coming now, and I am turning our U interaction. I have not shown you the Hubbard model, sorry, because you know what is Hubbard model. So, phase, this is the phase diagram at U equal to, at finite U. So, as I told you that at quarter filling at U equal to 0, as you turn on T prime, you find topological Fermi liquid to anomalous quantum Hall states. Then you can ask question, if you turn on U, what will happen? So, this calculation has been done using cluster perturbation theory and variational cluster approximations. So, you can see when the bands are overlapping strongly, and if you turn on U, nothing is happen. All any U, what you find is a metal. When you are here, when already system is in gap phase, and if you turn on U, it is obvious that U will not destroy the topology, and that topology is protected, and you can see here. But thing becomes interesting when you are close to this region where the band is not overlapping strongly. If you turn on U, what you find, this topological Fermi liquids goes to the quantum Hall state by applying U. This is a phase diagram at quarter filling of this model. Now I am showing you Hubbard model. So this is a Kitaev Hubbard model, and this P is just projected hopping along x and y and z axis. This model we have solved using cluster dynamical mean field theory. Cluster dynamical impurity approximation means you have a cluster. So what we do in VCA, we minimize the variational parameter, right? And cluster dynamical mean field theory or DMFT, we solve the problem iteratively. Cluster dynamical impurity is a mixture of minimizations and bath. So if you are solving the problem cluster dynamical mean field theory at 0 temperature, you have a cluster, and cluster is immersed in bath, and then you solve. So that's you all of you know more than me, because you have been listening to these lectures. So now this is the phase diagram, T prime versus U. When T prime equal to 0 is nothing but a graphene, and Asad has already created a wave, wrong wave, finding a spin liquid. So what is this? T prime equal to 0, you find semi-metal to antiferromagnets. But there was a paper in Nature in 2010 by Asad Fakhri, and he found spin liquid. Here we challenge that result, and we say that no, you cannot find a spin liquid in this system. So now I am going to tell you what I did. So this phase, this line we solved by the cluster dynamical mean field theory. The way, like, we do not allow any kind of magnetic order. So this is a solution of just paramagnetic solution. System goes from metal to paramagnetic insulator. So paramagnetic insulator in principle is a spin liquid. Now whatever you can do in cluster dynamical mean field theory about like construct a single particle object which breaks the time symmetry. So what we do, we allow staggered magnetizations. When we allow a staggered magnetization and ask what is U critical, so this U critical moved like this and turn here. So you find there is a region where a staggered magnetizations is 0, but system is still charge gapped. So whole this region up to infinity is a staggered magnetization is 0 and charge gap you have. So that we are calling a spin liquid, and this spin liquid is a special class of a spin liquid we call algebraic spin liquid. I will explain why I am calling algebraic spin liquid. You can see at T prime equal to 0, I told you that you keep changing T prime equal at 1 by root 3, system goes from 8 Dirac points to 2 Dirac points. So it starts from 2 Dirac points, spin degenerate Dirac points, then enter into the 8 Dirac points, then again it goes to the 2 Dirac point, but no spin degeneracy, and at T prime we have plotted just at up to T prime. You can see this, the 8 Dirac points survive even in the presence of interactions, and this is a Lifshitz line where you can find. And this line where you are going semi-metal, which this semi-metal breaks the time reversal symmetry. So I generally am confused what should I call, but I say this is a chiral semi-metal. So chiral semi-metal to algebraic spin liquid. So now I am going to show how should I prove that this phase is actually algebraic spin liquid. So if you ask what is the effective spin Hamiltonian at T prime equal to 1 for this model, what you will get is this. On even a small perturbations, it becomes a spin-spin correlation becomes a power law. So instead of a short range spin liquid, what you will have a algebraic spin liquid, means you have a spin-spin correlation power law. When we say algebraic spin liquid in the sense that it does not break symmetry, you cannot describe by the quasi-particle descriptions, and power law behavior should be there. So this happens when T prime equal to 1. Even if you just go away from T prime equal to 1, then this model will no longer be Kitaev spin model, it will be a Kitaev-Heisenberg model. This is not, this is a different Kitaev-Heisenberg model than the Khalilulin and all those they were doing. They are just adding Heisenberg model from outside. So this is a Kitaev-Heisenberg model which at when t prime is not equal to 1. You can also go any order by using some technique called perturbative continuous symmetry transformations. So this is we got up to the 4th order, this spin Hamiltonian. One good thing about this spin Hamiltonian is this, since we know exact solution of this and all these terms are small, then we can think about doing some mean field solutions for this H2 plus H4, treating H4 as a perturbation term. So how do we do this? So generally what you do is you solve the Kitaev model by introducing enlarging the Hilbert space. So at every site spin is residing in a 2-dimensional Hilbert space. But what Kitaev did, he introduced 4 Majorana fermion at every site. So he actually doubled the size of Hilbert space. And once you double the size of Hilbert space, you can express your spin operator in terms of a Majorana fermion. But remember this spin operator will be working in the, operating on the enlarged Hilbert space. And this Majorana fermion actually follows this algebra, Christoffel algebra, what you can see. So once you take this representation and substitute this in H2, what you can find that you will have a term like BB, and that BB which commutes with this Hamiltonian and commutes with each other also. So then you can solve H2 in the simultaneous eigenstate of this and Hamiltonian simultaneous eigenstate. So what you find, you can solve this problem because it turns out a quadratic, but since it operates, this C operator operates on the enlarged Hilbert space, you want a physical state. So how will you find a physical state? You have to satisfy these conditions after the solutions. If you satisfy these conditions, then you will find actually physical this. So what we did, we just applied that method and at the mean field level, and after doing all these things, what we found this spin-on spectrum as a function of u, and this Dirac point survive from infinity to 2. So at least if you believe that the perturbation, higher order perturbation is not a singular, then that perturbation is not going to destroy this Dirac point. So one thing I established that spin-on spectrum is a gapless. Then we do the calculations of spin-spin correlations. What we find is goes like a power law. So on that basis, we claim that this is algebraic spin. Other thing is this, that phase, the algebraic spin liquid phase, actually preserve the time reversal symmetry. But semi-metal phase, I just told that is time reversal symmetry is not there. So this is we can prove mathematically that algebraic spin in liquid phase is a time reversal symmetric phase. And here you are also seeing that if there is a chiral case, any possibility of chiral spin liquid for any u, then it should have gapped here. So I am going to now tell this how will you detect this geometric object in optical. So one more thing, this is just whatever the theme of a school, model to materials, this is opposite of that. This is a model to artificial material. So how will you detect Pancharatnam-Berry curvature? So suppose you know that we know all this semi-classical equation of motions for Bloch electrons in the presence of electromagnetic field. This equation holds at the 0th level, but if you go up to the gradient corrections, what you find a new term in your velocity, and that new term is nothing, it is Berry curvatures. So if you take this equation, which we call the Sundaram new equations, you solve this, you can find x dot, k dot, and then construct cloud density in Thomas Fermi approximations and use the Liouville's equations, what you will find is that as you remove the trap, this cloud will start rotating. If the cloud has a curvature, that cloud you can see the curvature by just cloud will start rotating. So, this is the one of the proposal how to we propose this how to detect the Pancharatnam-Berry curvature, but it also exists in the literature. Okay. So, this model is very interesting and many things we can explore, like a fractional quantum Hall state, what is the nature of a superconductivity. In antiferromagnetic phase, if you do the nonlinear sigma model, their half term exists there or not, and many other things. So, this is I want some people should take this model and do many more things. So, these are students and collaborators, and the works published, all 4 works, and the this work also and the PR to be published in PRV. Okay, thank you.
Thank you very much. Are there any questions? Yes, please.
This is a Sri Lakshmi Vishwanathan, Archana Mishra, Jean Paul here sitting there. This is R. Shankar. This is David Seneschal.
Sir, what are the qualitative changes of the results for 1 dimension and 2 dimensions?
Where? I am not thinking even about 1 dimension. I don't live in 1 dimension. So this is everything in 2 dimension.
Okay. And one more question, how the Chern number varies with that Hubbard U?
No, so Chern number is a topological object. It cannot vary. Either it will be there or it will be destroyed. So that is the meaning of topological object. You can ask geometric object. Always you will have a geometric object in projected Hilbert space. That can change with VU. But once it acquires a topology, it will be either it will be destroyed or it will be there.
But I think that's the question is there a topological phase transition as I vary U? Are there critical U's at which a Chern number changes discontinuously?
Yeah, there is an example in literature.
But in this particular model?
No, it is not. No, in this not.
Okay,
So Karin Lehur and her students, they did a calculation using a CDMFT in Ken-Millie or honeycomb lattice. That paper you can see, they discussed in quite detail. But what you can ask, when you Chern number, if you ask Chern number can change like this, I gave you the 4th kind of a phase transition. If you take a topological states, you apply some kind of a perturbations and it can enter into the other topological state. So, if you suppose this state has a Chern number 1, it can go into the Chern number 2, Chern number 3, but it still will be a Chern number, discrete value.
Are there any more questions? Antoine.
Let me make sure I understand your proposal for experimental observation. So basically what you propose is to stabilize a state where there is a non-trivial Berry phase, and then to remove the trap. So I suppose we are talking about cold atom system.
Yeah.
And then this will induce spontaneous rotation. This is what you're saying?
So we in the paper, this paper, we wrote in quite detail. This just I think Lakshmi has just updated. I did not know that paper has already published in PRV.
So no, this is not a physics question. Pancharatnam, was he before Berry?
In the 1954 Pancharatnam or 1954 or 1955 exactly, I don't know the date, but he discovered this phase in classical optics. Then Berry came here in Bangalore in 1987 and gave a talk Pancharatnam by calling Pancharatnam-Berry phase. So that's why I am using, and Berry has written a paper in somewhere journal in optics journal. What is the? Can you tell Lakshmi what is the journal name? Lakshmi is not here. Huh? Journal of Modern Optics. The name is Pancharatnam-Berry curvature. So that's why I'm taking that name, because one of the referee asked, why are you using the Pancharatnam-Berry phase or Berry curvature?
Maybe one last question. You mentioned this presence of a spin liquid that Safaka Hassan got for
Yeah.
the hexagonal lattice, and there has been a lot of discussion about the presence or not. It seems that now at least the numerical people agree that this phase is not there.
Yeah, that one of the guy I am Hassan.
It's you, right?
Yeah.
Now I got it. Very good. Now we are. Now you said it. Okay. Very nice. Very nice. There's a last question there.
So I may have missed this. The Heisenberg interaction, is it always antiferromagnetic or can it be ferromagnetic?
It can be ferromagnetic if you go T prime more than, I think, I don't know, 1.5 or something.
Oh, okay. Because
So
I think
even a T prime, if you take a T prime up to infinity, many funny thing comes. So that's why I just took the phase diagram of T prime equal to 1. It becomes ferromagnetic.
Okay. So thank you very much. With that, we thank you again, and we conclude this session.